This is Radio Eco Shock with Alex Smith.
When it comes to sea level rising by feet or meters, the biggest fear is melting mountains of ice piled up on Antarctica. Recently, NASA scientist Eric Regnault told us those glaciers are melting 6 times faster now than in the 1950s. In another just published paper, scientists discovered the marriage of 2 forces making that happen. This could determine the future map of the world as disastrous sea flooding invades farmlands, cities, and whole nations. The science is challenging. It involves a 34-million-year history of Antarctic ice, tiny single-celled animals, carbon dioxide, and the astronomical place of Earth in space, all of that. Fortunately, we have the lead author, Dr. Richard Levy, here to help. Dr. Levy is a paleoclimate scientist and program leader at New Zealand's GNS Science, a government crown corporation, I believe. Levy is a veteran of scientific expeditions to Antarctica, with many papers about the coldest continent on Earth. From Wellington, New Zealand, Richard Levy, welcome to Radio Eco Shock.
Thanks, Alex. Thanks very much for having me.
How many times have you been to Antarctica, and is there a specific base or ship used for your research?
Oh, gosh, I've been to Antarctica now 12 or 13 times, 13 seasons down there. I actually started my career through the United States Antarctic program. So I was doing my studies, my doctorate degree at the University of Nebraska, and first went down to Antarctica from America, which is sort of strange, really, given that I'm from New Zealand. But yeah, so I've spent quite a bit of time working with the US program, but also spent some time more recently working through the New Zealand Antarctic program based out of Scott Base. Both of them are on Ross Island. Both of those bases are not too far apart, but run by different countries and run in quite different ways, to be quite honest.
And there is a big stretch in this new paper. Why did you and Stephen Myers from University of Wisconsin-Madison need to connect those tiny creatures, which I'll call forams for short, to the astronomical position of Earth out in space?
Yes, so as you've mentioned, our research focuses on the long-term history of the Antarctic ice sheet. We want to understand when it expanded, when it grew larger than today, and when did it retreat or collapse and get smaller, and fundamentally what caused these changes. We use this knowledge of past ice sheet dynamics to improve computer models that allow us to project future change and determine likely rates and amounts of sea level rise. We're particularly interested in marine-based sectors of the Antarctic ice sheet, areas where the ice sheet sits on the ocean floor, as these regions are vulnerable to increases in ocean heat, and that's something that Eric Regnault's recent study has shown to be true, that these areas of the ice where it sits on the ground below seafloor are particularly susceptible, particularly vulnerable to changes in ocean heat. So our research is really sort of trying to take the longer-term perspective of what Dr. Regnault has observed recently. We've known for a long time that changes in the way our planet orbits the sun affects climate. The shape of our orbit changes from oval or egg-shaped to more circular and back again, and this takes place every 100,000 years. This is this natural cycle. We also know that the tilt or slant of the axis around which our planet spins every 24 hours changes from steep to less steep, and this happens every 40,000 years. So again, these interacting natural cycles affecting our climate. So high tilt causes more energy from the sun to directly reach our polar regions, and this has a huge impact on the ice that sits there. Obviously, more solar energy coming in and hitting the ice sheet will cause it to melt. Now, we've known that these changes drive the ice ages, and we've known this for a long time. Research back in the 1800s and into the early 1900s showed us that these changes actually cause our ice ages. But the details regarding exactly how these astronomical shifts affect the ice sheets, they're not really well known at all. So in our study, Stephen Myers at the University of Wisconsin and myself and our co-authors, in our study we examined data from ocean sediment cores. Natural chemicals preserved in the layers of ocean sediment, preserved in the shells of organisms that live in the ocean, tell us about past changes in ocean temperature and ice volume. Now, we noticed there were intervals of time when the ice sheets became much more sensitive to changes in Earth's tilt. These intervals of increased sensitivity to tilt, or what we call obliquity sensitivity, happened during times when large areas of Antarctica's ice sheet first advanced into the ocean. So the first time from all of our geological studies that we see ice sheets stepping into the ocean, expanding into the ocean, then these deep-sea chemical records of climate change become much more sensitive to changes in the tilt. So we noticed this relationship. At this time, when we noticed this increased sensitivity, proxy data tell us that atmospheric carbon dioxide levels generally range between 400 and 600 parts per million. This is pretty key because these levels are like those we have today and also very similar to those projected for the next several decades. But these results suggest that changes in ocean heat around Antarctica's margin respond to changing tilt. When the ice is in the ocean, it responds to tilt. It's much more sensitive. These variations in ocean heat have a major impact on Antarctica's marine-based ice sheets. Now, we also noted that the sensitivity to ocean heat change decreased during times when CO2 dropped. Now, this is really important. So, sensitivity increases when CO2, in the past, when CO2 was above 400 up to 600 parts per million. The sensitivity to ocean heat change decreased during times when CO2 dropped to pre-industrial levels, so dropped sort of down below that 300 parts per million. Sea ice grew and expanded across the Southern Ocean, so this is pretty critical. Sea ice appears to act as a buffer or a barrier to ocean dynamics. So right now, today, we have a persistent sea ice, a lot of sea ice around Antarctica, and it seems that this expanded sea ice is sort of buffering or protecting the marine-based portions of Antarctica's ice sheet from heat that would otherwise be driven up onto the continental shelf due to our relatively high tilt that we're at today. Sorry, Alex, I've just carried on talking. You probably have a few questions.
I have lots of questions from that. First of all, it's fantastic science that really you can reach into what may be microscopic organisms buried in the seabed and pull out isotopes of oxygen, basically molecules, and know from that whether ice was growing or shrinking or there at all. Is that what you were doing?
Yeah, that's right. And that's not just our research. That's a huge global effort that's been going on for a long time where scientists have been looking at these marine organisms, the chemistry of these marine organisms and the isotopes captured, which change as ice volume and temperature changes on Earth. So you have this long-term history acquired from deep-sea ocean sediments that tell us something about what the ice sheets were doing and something about what temperature was doing. The challenge with those sorts of records is that they're not direct archives of ice sheet variability. So you actually don't know absolutely for sure that the ice sheets were growing and advancing. You've got a pretty good clue from the changes in chemistry. But what we did was take those records from the deep ocean, run some mathematics, statistical analyses on those records, and we noted changes in patterns through the isotope record. And then we compared that directly with records from the Antarctic margin, which is sort of an area that I've focused most of my research on, myself and colleagues, where we actually see direct records of ice sheet advance and retreat. What we noticed was that during times of high sensitivity to changes in the tilt, they correlated or matched with times where we see evidence for ice sheet advance into the ocean. So that gave us some indication that there must be a connection between times when the ice sheet was in the ocean, connected to the ocean, and an increase in sensitivity to the tilt. So this ocean ice connectivity became apparent because we compared the deep-sea records, the planktonic records of climate change with direct records of ice sheet advance and retreat.
If I go to Wikipedia and look up axial tilt or obliquity, I learn we are halfway through a 41,000-year cycle and we're heading towards decreasing tilt. And according to Wiki, that should mean a cooling phase with more Antarctic ice is in the planet's future. So, a doubter would ask, why is Antarctica melting in what should be a cooling phase of the Earth's tilt?
That's right. So it's not just the tilt that causes the climate to warm and cool. It's also the shape of the orbit, or what we call eccentricity, as well as precession, which is wobble of the Earth's axis like a spinning top. All of those things interact to drive the ice ages. And so if you look at Wikipedia, it's correct. We've passed through a point of high tilt and we're heading back towards an interval of low tilt. And so based on what we've studied or we've discovered, we should be heading toward a time where changes in the Earth's tilt actually cause the ice sheets or allow the ice sheets to grow if it was just obliquity driving the climate. But what we also know is that when carbon dioxide levels go above 400 parts per million, then the oceans themselves, the average climate state on Earth gets to the point where you can no longer maintain extensive marine-based ice sheets. So in this case, carbon dioxide essentially is going to override the cooling effect of the change in the tilt. But what we're suggesting in our research, and what's really critical, is that it also appears that sea ice, or the presence of sea ice, buffers the ice sheets from ocean dynamics, from the warm ocean. When you warm climate, warm the atmosphere, warm the oceans by driving CO2 up, we are likely to lose that sea ice. And because we're still in a relatively high tilt, the astronomical forcing, that climate warming driven by a relatively high tilt, will actually amplify any warming that's happening because of the CO2 increase. And so on human timescales, in terms of what we're doing today to the planet, we're suggesting you'll see an amplification of any warming because of this natural warming due to high and cooling due to low tilt. So because we're in a relatively high tilt, we're going to amplify the warming. Now, if we can wait 10,000 years or so, then the change in tilt to a higher tilt, so that less energy reaches the poles, could actually reduce some of the warming. But that's going to happen on a very, very, very slow, long time frame. And of course, in the meantime, CO2 is high, and we're actually jumping back millions of years to a climate we haven't experienced since 30, 35, potentially 40 million years ago.
Is your 34 million year reconstruction of the history of Antarctic ice sheet, is that new to science, or is it a compilation of earlier work?
Oh, look, I would say it's a compilation of earlier work. We've managed to pull together a whole bunch of records in a way that no one's done that before. We've analysed those records in a fairly unique way, and we've put essentially two people or a group of people together in a room to look at those data in a different way. So it's sort of it's a unique way to look at the history, and it's a unique integration of data sets.
When I look through the long history of that polar continent, we make a surprising discovery. There was a mass extinction event in the middle Miocene period, about 14 million years ago, say. But this time the killer was not global heating, as has happened so often in past mass extinctions, but it was a rapid cooling. Can you tell us what happened?
A mass extinction. I have to say, Alex, I'm not too sure what you're talking about.
Well, there's another Wikipedia gem. It talks about the Middle Miocene extinction event around 14 million years ago. I'll send you the link and see if I can find out more myself.
I know I've just actually finished reading the book by, I can't remember the name of the author, The Sixth Extinction, won the Pulitzer Prize, I should remember her name, which I found quite fascinating because my colleagues and I are also very interested in drivers of large-scale turnover in the biotic system, in particular the plankton in the ocean. What we do notice is that there, in the Southern Ocean, this is another piece of research we've done, in the Southern Ocean, if we look at the diatoms, these marine algae that live and dominate the Southern Ocean today, there are periods where their turnover is much more rapid than others. So we actually see increased speciation and increased extinction, and it seems to be periodic. And that actually coincides with this so-called mid-Miocene extinction event you're talking about, but we actually see it as a turnover pulse. So it's extinction and speciation. Our inference is that turnover was driven by global cooling. As CO2 dropped below a certain threshold, sea ice expanded and caused geographic stress in a way, or ecologic stress on the diatoms. And so cooling can drive these turnover events, but it wasn't a mass extinction in the sense that the Cretaceous loss of the dinosaurs is a mass extinction. It's a perturbation in the biological system that seems to be episodic, periodic, all the way through that sort of, at least from what we can tell, last 20 million years or so.
As you've mentioned, a key factor in this time of human-induced rapid warming is the existence of sea ice around the perimeter of Antarctica. Until 2014, that sea ice seemed pretty healthy, maybe even growing. What is the state of sea ice there now?
Yeah, so it's been a bit of an anomaly, I guess, where people have looked at the Arctic and the observations indicate we're losing Arctic sea ice fairly rapidly, and the counter to that was that the Antarctic sea ice was expanding. And in fact, over the last 2 or 3 years, the satellite observations are showing us that we're rapidly losing sea ice extent in the Antarctic, and I think this year has been the same. Some of my colleagues are sea ice experts and are certainly concerned about the current pattern, but of course the time series is relatively short. We've only got 3 or 4 years of data to show that the Antarctic sea ice is decreasing, but certainly from our point of view, from our study, we'd be concerned. If we lose that sea ice, many things will happen, but one of them could be that the warming around the margin, due to the increase in CO2, but also due to the fact that we're at a relatively high tilt or a moderate tilt, will amplify warming up onto the shelf, and that will cause marine-based ice sheets to retreat. So I guess, in a sense, from my perspective, we certainly don't want to see further loss or experience further loss of that sea ice. I don't think it would be good at all.
So a second major piece of science about Antarctica has just been published in January 2019 in the Proceedings of the National Academy of Sciences. Recently, I interviewed the lead author, Eric Rignot, for Radio EcoShock. How does that paper relate to your latest work?
Yeah, well, we're all interested in understanding ice sheet dynamics, I guess, on different timescales, and Dr. Rignot's work is critical for our understanding of what's happening today and over the recent past. Those satellite time series, those satellite data he's analysing show us that we're losing mass, or that the Earth system is losing ice mass, that Antarctica is losing mass, and it's accelerating. And to be quite frank, that's concerning. I've read that piece of work, and it's something that certainly doesn't help me sleep easier at night. Now, what we're showing, again, is that those patterns that Dr. Rignot and his colleagues are observing, if you look over the long term, anytime climate warms due to CO2, due to orbital features, then the oceans tend to warm around Antarctica, and the first thing to start experiencing melt, or the first parts of the ice sheet to start experiencing melt, are those parts that sit in the ocean. They're vulnerable to changes in ocean heat, and that's certainly something that we've observed from the past. We're observing it as it happens today, and most of our computer models that are informed by these past data sets also show that those areas of marine-based ice sheet are highly vulnerable to melt, and other bits that are going to go first, and that's certainly what we're observing today.
Yeah, I can recall about 15 years ago talking with scientists who basically described Antarctica as an inert slab of ice that would be there for hundreds of thousands of years, and that would be the last to go. But that doesn't seem to be the case now. No,
that's the key outcome of all of these studies, is that Antarctica seems to be way more sensitive to climate change than was previously thought. As you say, people have assumed that large chunk of ice sitting down in Antarctica is cold, inert. It feels very little from the rest of the world, but boy, we're learning that that's the opposite. I know when I was doing my studies many years ago for my doctorate, my advisor was saying, look, this ice sheet is way more sensitive, way more vulnerable than many geologists at the time were saying, and it seems that he was onto something. Before him, John Mercer from Ohio State, back in the 1950s, early 60s, wrote some papers, one of which was published in Nature, saying that if we continued putting as much CO2 into the atmosphere as we were currently doing back then we'd lose West Antarctica, the marine-based ice sheets of West Antarctica, and that sea level would go up by 3 to 5 meters. And he did this 50, 60 years ago. And again, what we're learning today shows that he was right.
Why isn't Antarctica warming as fast as the Arctic?
Yes, okay, so there's a feature in the Earth system called polar amplification, where the polar regions tend to warm much faster than the tropics. Average temperature goes up by, let's say, 5 degrees. The tropics may go up by 1 slightly. They can't really warm that much, but the polar regions can. And the Arctic's certainly experiencing that amplification right now. We're observing it. The Antarctic has been sort of delayed, and part of that could be due to the ozone hole, the cooling effect of the ozone hole. We're still really trying to understand polar dynamics, but the expectation is that at some point that amplification will kick up in the Antarctic as well. Certainly around the Antarctic Peninsula, the rates of warming are high, and as high as one might expect. But over the whole of Antarctic, you're right, it hasn't quite amplified as much as the climate models even expect. But who knows, as the ozone hole anneals or heals, maybe we'll get a sudden little kick in the system that we're not really prepared for.
Should we presume there was no ozone hole over Antarctica in the millions of years that you looked at in your records? Is it entirely a man-made phenomenon?
Yeah, I am not the expert. I certainly shouldn't be commenting on that. But if there's a fundamental principle we apply in geology called the present is the key to the past, and certainly my understanding is that the current ozone hole has been driven by human activity, by the CFCs, but I couldn't say for sure whether there was an ozone hole in the past or not. Yeah, so I guess I assume there likely wasn't, because the thing that caused it recently, certainly we weren't around to do it millions of years ago, that far back in time, but I can't say for sure.
Okay, so you're in New Zealand. Is your country's capital, Wellington, on the list of cities under threat by rising seas if Antarctica really does release its ice?
Absolutely. I actually head up with a colleague program looking at sea level rise around New Zealand, taking the research we've learned, or taking the research we're doing in Antarctica, the things we're learning, and applying them, what we call downstream, to New Zealand, but also to the rest of the world. And Wellington certainly is an area that is under threat from sea level rise. In fact, if I get the numbers right, I think a 10 centimetre rise in sea level by 2100, if it was as small as that, increases our risk of flood frequency from a 1 in 100 year to an annual event. It's something like that. So small amounts of sea level rise have a big effect on Wellington. Yeah, something we all need to be thinking about and planning for, adapting to.
So what is New Zealand's role in Antarctic research, and does the government fund that?
The government does fund it, yes. We're very lucky in New Zealand. Our government invests money to have or supports a base down in Antarctica. So New Zealand has its own base where we can from out. So New Zealand has its own base out of which we can conduct our research. We've also been fortunate in the recent times, the government's acknowledging the relevance and importance of Antarctica, and has just invested in what they call a science research platform, or a science platform. It's being directed by Dr. Nancy Bertler, and it's a real opportunity for us to take some big steps forward in our understanding of the past and future response of the Antarctic ice sheet to climate change. So we're very excited that our government recognises the value and is putting energy and effort into allowing us or enabling us to do research in Antarctica.
You're listening to EcoShock Radio for the world.
I'm Alex Smith. Get it all at our website, ecoshock.org. From New Zealand, you're listening to Dr. Richard Levy on Radio EcoShock, and we're talking about new science about the melting of Antarctica. With all our technology, Antarctic exploration is much safer now than in the days of Scott and Amundsen and Shackleton. But when you go there, do you still get a vision of that dangerous nature that's there at the extreme end of the Earth?
Boy, I've thought about this quite a bit. Lying in a tent down in Antarctica during the middle of a storm is certainly a bit unsettling. You sort of hope your tent holds and it's not going to blow away, and you go the way that Scott did. But I think I can't compare what we do today to what the early explorers put themselves through. I mean, when I leave New Zealand, I get on an aircraft and, 5.5, maybe 7 hours later, I'm in Antarctica. I've got ModCon gear, high-tech gear that's designed to keep me warm as well as be functional. Now, when Scott and Amundsen and Mawson and some of the heroic figures of previous Antarctic research or early Antarctic research and exploration are concerned, they got on a ship, had to sail off into the distance. 2 years, 3 years later, they might return, and chances are they might not. So from that point of view, I think we're very lucky today that we get to go down there. It's pretty efficient, pretty quick, and we're very well looked after. Having said that, you're out in the wild. Storms come through, accidents can happen. So you're always having to, consider where you are, work carefully, Be safe, yeah. I mean, just as anywhere else in the world, you might be out in the wilderness, paying attention to your surroundings and just taking care of yourself. Now, of course, in Antarctica, one of the benefits, if you're wanting to be safe, is there aren't any wild animals that you have to be too concerned about. Where I work in the mountains, there's essentially no life at all. So it's really just the weather and your colleagues doing silly things if they happen to do something silly and you have an accident. The other two main things you have to worry about. The isolation, if you're in the deep field, sometimes you can be, 2, 3, perhaps a week away from help if the weather doesn't behave itself. So, there are certainly risks, but I think the risks are just so much smaller than back in the day when those, what I might consider fairly crazy individuals, sort of booked onto these ships and headed off into the distance.
Crazy but brave. So what's next for you in research?
Boy, it's a good question. I think there's so much we still need to learn and understand about the Antarctic ice sheets. I mean, we're scratching the surface. We're learning a lot. We're certainly able to simulate using computer models the response of the ice sheet to various forcings, but we know that they're far from perfect. There's still major questions about the rates at which the marine-based ice sheets will retreat and by how much. Every time we look at the ice sheet, as Eric Brignot's research and our research shows, we learn more, and everything we learn suggests that the ice sheets again are different to what we previously thought. So understanding the long-term history, looking at past intervals of warmth, certainly key. One of the big projects we have on the horizon is an attempt to go much closer to the centre or to where the current West Antarctic ice sheet sits on the seafloor, right at what we call the grounding zone, and actually drill a hole right next door to the West Antarctic ice sheet to see whether or not it disappeared during very recent intervals of warmth, intervals of time when climate was similar to those we're trying to achieve through the Paris agreements. If we can mitigate the carbon emissions and keep warming below 2 degrees, is that enough? Did the West Antarctic ice sheet actually disappear anyway, even if we can keep warming below 2 degrees? We're actually not 100% sure. Data from around the world suggests that at that amount of warming, 1.5 global average, sea levels were 6 to 9 meters higher. So that sort of suggests that the ice sheets disappeared even under Paris targets. Now, whether or not that's true, at the moment we're relying very heavily on models. We want to get data from the center of the ice sheet, right where the action happens, to try to say, yes, it does disappear or did disappear the last time Earth was that warm, or no, it did stick around. So I think that's probably one of the highest priority research areas for us is, what does the ice sheet do under 1.5 to 2 degrees warming scenario? Does it stick around? Does it disappear? Models suggest it's sensitive, but we want to know for sure. It's understanding what it'll do with respect to all of those people that you mentioned, walking around, living around the coastal regions of Earth. I mean, they're really depending on us knowing what the Antarctic ice sheet did the last time it was 1.52 degrees warmer than present. That's the priority.
From Wellington, we've been speaking with Dr. Richard Levy, and he's with New Zealand's GNS Science, and he's the co-author of the paper Antarctic Ice Sheet Sensitivity to Obliquity Forcing Enhanced Through Ocean Connections, as published in Nature Geoscience 2019. I'll put links to the science in my show blog at ecoshock.org. Richard, thank you for sharing your valuable Down Under time with us.
Alex, thanks very much for taking the time to call. It's been a pleasure.
Check out the Radio EcoShock website. We're at ecoshock.org.